In 2016, at a recycling plant in Japan, researchers noticed something unusual. A colony of bacteria was growing directly on the surface of a discarded plastic bottle. That plastic, PET or polyethylene terephthalate, wasn't supposed to biodegrade, and yet it was vanishing. The bacteria was digesting it. Plastic is everywhere, and one reason it's so widely used is exactly why it's so hard to get rid of. PET is a polymer, a long chain made by repeating smaller chemical units called monomers. In PET's case, these monomers are ethylene glycol and terephthalic acid, linked into tight, orderly strands. These chains are stable. They don't break easily under light, oxygen, heat, or microbes. That's what makes PET perfect for bottles, food packaging, clothing, and more. It resists water. It doesn't rot. It doesn't deform easily. It's cheap to make and transport. But that same durability, chemical and structural, is a disaster once the product is thrown away. PET can persist for hundreds of years in landfills. In the ocean, it breaks into microplastics, particles that can enter the food chain and accumulate in living organisms. We designed a near-perfect material, and then we lost control of it. Then came a surprise. In 2016, a team from the Kyoto Institute of Technology published the genome of a bacterium they named Ideonella sakaiensis. This microbe produces two key enzymes, PETase and metase. Together they break PET into its original monomers, ethylene glycol and terephthalic acid, which the bacterium can then metabolize. It doesn't just coat the plastic, it breaks it down at the molecular level and uses it as food. At first, this process was slow. PETase works best at moderate temperatures. In nature, degradation takes weeks, even months, far too long for industrial use. But researchers saw potential. In 2018, a team in the United Kingdom engineered a variant of PETase with improved efficiency and thermal stability. It worked faster. In 2020, another group combined PETase and metase into a single fusion enzyme, increasing the breakdown rate even further. Some engineered strains now degrade thin films of PET in less than a week. Why does this matter? Most plastic recycling today is mechanical. It involves melting and remolding, which downgrades quality over time. But enzyme-based recycling, called enzymatic depolymerization, breaks plastics down to pure monomers. These can be reused to make new plastic with no loss in quality. It's cleaner. It works at lower temperatures, and it could process plastics that mechanical recycling can't handle. Several biotech startups are now building reactors that use these enzymes at scale. It's early. Current capacity is small compared to global plastic production, which exceeds 300 million metric tons per year. But the path is clear. Instead of burying plastic or burning it, we can dismantle it chemically and reuse it. Not all plastics can be treated this way, not yet. But for PET, it's a promising start. We created a material nature couldn't handle, and now nature is catching up. A microbe, evolved in a waste dump, may help us solve one of the messiest problems of the modern world, not by undoing what we made, but by learning to take it apart.